Hi, hello, welcome to Mickey Techie. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement of creating these kinds of technical videos in public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore, for igniting me a spark of creating these kinds of technical videos in public domain. And I would like to thank Almighty my God for my good health and broad mind. And I would like to thank my friends, followers, my dear students and subscribers for their continuous support. Today's topic of interest is radiation. We know that there is a three mode of heat transfer. One such mode is called radiation. And the other two modes are like a convection. So for the conduction, the material to material with the contact of the materials or molecular vibrations, the heat is being conducted. Whereas the convection is the heat conducted between the two different phases. The phases called solid to liquid or liquid to gas or solid to gas, like that. It is called convection. In the radiation, like, there is no intermolecular vibration or there is no phase change, there is no phase difference. It is in the form of an magnetic waves. The energy is emitted. Heat energy is emitted. So that is called a radiation. The best example of a radiation, we know that the sun is far away from the earth, but still the heat, we can feel it. The heat of the sun, we can feel it. So this heat transfer is called as an radiation. A best example is this: whenever a day, a bright day, an afternoon, we are walking in the streets or we are riding in a bike, we feel the heat from the sun. So how it is happen? Is there any substance between the sun and the earth? It is a space, it is a vacuum between the earth and sun, but still we are feeling the heat. So what we have understand is there is no medium for radiation. So that is the understanding. That is our understanding about radiation. There is no need of any matters or any space for the radiation. So here I would like to give a picture about the modes of the heat transfer. Here you can see the three modes of heat transfer. Just for an example, we are heating a water at a container. If we hold the container in our hand, what happened? We can feel a heat. So that is called a conduction. So heat is transferred from the flame to the container, and this container, it is a metal. So metal to metal heat transfer, that is called a conduction. And the metal is filled, the container is filled with liquid. So the metal, here it is a metal to liquid heat transfer, this is called convection. So metal is a solid, we know that. Liquid, it is another phase. Solid is another phase. So heat transfer between solid to liquid, so that is called convection. And if you are near to the heat, if you are near to this flame, we feel some of the temperature is feeling in our hand, so that is called a radiation. So this is the best example of having three modes of heat transfer in a single step. So the radiation is the thing without having any intervening medium, the heat is being converted means it is called a radiation. We know that the flame is in somewhere else from the distance, but still we are feeling the heat. So how it is coming? By means of an uh, radiation, that is electromagnetic waves. So with this information, I would like to start my content for about the radiation. First, it is the energy emitted by matter in the form of electromagnetic waves is called radiation. In radiation, the internal energy of the object decreases. So we have to correlate with the thermodynamics. So the internal energy of the object is decreased. Next, the emission of thermal radiation is depends upon how it is depends upon what is the factor where the thermal radiation, where the electromagnetic waves will pass. So one basic thing is there for heat transfer, if we need a space, two spaces, so say this is one, this is two, this is have temperature 1, this is have temperature 2. If there is any temperature difference, if there is any temperature difference, I say T1 is greater than T2, then the heat energy is transferred from T1 to T2. So this is the understanding of heat transfer. So heat transfer is according to the second law of thermodynamics, where the higher energy level to lower energy level, the heat transfer is being done. Okay, so the emission of the thermal radiation is depends upon nature, temperature, and the state of emitting surface. What is the state of emitting surface? Whether it is an heat or something else. So that is the thing. It depends on this. So I said state of emitting surface means either a wavelength or a frequency of radiation. That is the important. Here, for the gases, dependence is also upon the thickness of the emitting layer and the gas pressure. So this is also very important. For gases, the gas pressure and the emitting surface thickness is also being needed. And next, the thermal radiation exhibits the characteristics very similar to those of visible lights. How the light is being glowed, like that the thermal radiation is being glowed. Thermal radiation can be refracted, and are subjected to scattering and absorption when they pass through a medium. So this thing is similar characteristics to the light. The light can be reflected, refracted, and scattered and absorbed. Similarly, the radiation can be reflected, refracted, and scattered and absorbed. Reflected means it can be transferred to either any direction. Refracted means can be displaced, and scattering means it is also we are scattering the waves. Absorption means the energy is being absorbed. The property of the emission, surface emission, the property of surface emission, the rate of surface emission of the radiation of the body is depends on, as I said earlier, temperature of the surface, nature of the surface, and wavelength or frequency of radiation. So these things are the properties of surface emission. These things are very important in order to calculate the radiation. temperature difference should be needed, and nature of the surface means what type of body it is, what is the emissivity of the body. These things are very much needed. This radiation is being explained by many peoples like Planck's law, Stefan Boltzmann law, Weins law, Weins displacement law, Kirchhoff law, Provest theory, Lambert cosine law. Like that, the thermal radiation is being studied and examined by very many scientists, and all the laws which we are going to discuss in this lecture. So please be careful on this nature of the surfaces. The every law, the nature of the surface is very important. How the body behaves, so that is very important for finding the thermal radiation. So here the emissive emissive power is very important for the radiation. So here I am going to start Stefan Boltzmann law. First we are going to understand the importance of the Stefan Boltzmann law. The Stefan Boltzmann law is derived from Planck's law. This thing you have to understand. The Planck's law is the mother of all radiation laws. Okay, Planck's law. So Planck's law is a basic law which the other laws are derived from the Planck's law. So one such law is Stefan Boltzmann law. So Stefan Boltzmann law is also called as total emissive power E. Here we are going to find total emissive power E. And I would like to give a glimpse the total emissive power. It is directly proportional to temperature. So temperature. So the definition what it says is the total emissive power is defined as the total amount of radiation. Total amount of radiation means at all wavelength range radiation. At all wavelength range radiation. Either it is a short wavelength or long wavelength emitted by a body per unit area and time. So that is the total emissive power. The emissive power is the integral of 0 to infinity emissive power of the body into d lambda, and therefore the equation can be derived by a sigma into t power 4, that is watt per meter square. So this is the emissive power, where the sigma is the Stefan Boltzmann constant. It is 5.67 into 10 power minus 8 watt per meter square Kelvin power 4. So this is the constant you have to remember. Okay, therefore we know that emissive power and heat transfer, the radiative heat transfer Q is equal to sigma A into T power 4, that is what? Sigma A T power 4, that is what? The emissive power of a black body. So here the Stefan Boltzmann law is always considering a body, a highest emissive body as a black body. Therefore, they are calculating about the black body. Even Planck's law is also considering for the black body. Black body is very important. The color structure is in black color. Very simple. A color structure is in black color. For your example, you may feel when you are wearing a black shirt and black pant at the very high summer, if you can easily feel the heat of the sun. Whereas if you wear a white shirt or white pant, you cannot feel that much of heat when compared to the black shirt. What is the inference is the black body is a very good radiative body. That is why the nowadays the two-wheeler engines are mostly in black color. Why it is black color? The radiation, the heat transfer, better heat transfer can be achieved in the black bodies. So that is why they are using the black bodies. Okay, so here, the Stefan Boltzmann law, the emissive power of a black body is proportional to absolute temperature to the fourth power. That means what it indicates, the emissive power of a black body is directly proportional to temperature power 4, and we know that the proportionality constant is the Stefan Boltzmann constant, sigma into T power 4, where sigma is the constant, Stefan Boltzmann constant 5.67 into 10 power minus 8 watt per meter square Kelvin power 4. So this you have to understand. For the entire spectrum, the wavelength, for the entire spectrum, the lambda is the wavelength. The lambda is the wavelength for the entire spectrum. It is greater than 0 but less than infinity. So here we are mostly the emissivity. The emissivity is always depends between 0 to 1. Here the lambda wavelength. The lambda is the wavelength where eta is the emissivity. Emissivity means it is 0 to 1 where the wavelength is 0 to infinity. What it means that whatever may be the wavelength, either it is a short, medium or long wavelength, this is the equation. So that is the thing you have to understand. Next, emissivity. Emissivity is the ability of the surface of a body to radiate heat. And another definition we can say, the emissive power of a body to the emissive power of the black body is called emissivity. So emissivity is generally indicated in eta. So eta is equal to emissivity of the body divided by emissivity of the black body. So emissivity, it is between 0 to 1. This you have to remember. So the real surface, whatever the real surface, if we want to apply the Stefan Boltzmann law, the emissive power of the real surface, is equal to eta sigma A T power 4. So this is the, if not A means it is emissive power. If heat transfer is there we have emissivity sigma. If it is a heat transfer, Q is equal to emissivity area sigma, that is Stefan Boltzmann constant, into T power 4. This is the heat transfer where emissive power, that is capital E, is equal to emissivity sigma T power 4. So this you have to understand. And we have some points to remember. For the black body, the emissivity is equal to 1, whereas for the white body, the emissivity is equal to 0. For gray body, it varies 0 and 1. It varies between 0 and 1. The emissivity may vary with temperature or wavelength. This you have to understand. Emissivity may vary with the temperature and or wavelength. Where diffuse means it is the property or independent of direction. A diffused body is called the direction is independent, and gray body, its property are independent of wavelength and temperature. Gray body property is independent of wavelength and temperature. And next, irradiation. The emissivity, irradiation, radiosity, these things are very very important for studying about the radiation. Irradiation means the total incident radiation on a surface from all direction per unit time and per unit area of the surface. So if I say this is my surface, at this minute, at this second, how much of the intensity of radiation is being transferred? So that is called irradiation. Where radiosity is the radiant energy leaving a surface per unit time. So how much radiation is leaving? That is called radiosity. Irradiation means absorbed total incident radiation on the surface from the direction, from all direction. So from all direction if it is coming, so that is called irradiation. If the radiation is went out from the body, that is called radiosity. And this radiosity, the radiosity, the radiosity, it is indicated in J, which is equal to emissivity plus the reflectivity of the body into irradiation. So the radiosity is equal to sum of emissivity plus sum of emissivity and the product of irradiation and reflectivity. So that is the another definition of radiosity. The total incident radiation is QA is equal to heat by absorption plus heat by radiation or radiation plus heat by transmissibility. These three things are being important. So absorptivity, radiosity and transmissibility, these three things are very very important. So what I'm going to do is, here I'm making this QI incident radiation to the denominator. What will happen, that is 1 is equal to QA by QI plus QR by QI plus QT by QI. Therefore this is nothing but 1 is equal to alpha plus rho plus tau, where alpha is the absorptivity, rho is the reflectivity and tau is the transmissibility. What we have identified is the sum of the total incident radiation is equal to 1. The sum of total incident radiation is equal to 1. Whatever may be the body, the total incident radiation is equal to 1. So this you have to understand. For the black body, absorptivity is equal to 1, where reflectivity is equal to 0 and transmissibility is equal to 0. For white body, absorptivity is equal to 0, radiation is equal to 1, transmissibility is equal to 0. For the transparent body, the transmissibility is equal to 1, absorptivity and radiation is 0. And for the opaque body, the transmissibility is 0, where absorptivity plus radiosity is equal to 1. So this you have to understand very clearly. Next, a very very important law is a Kirchhoff law. It's so this is the Kirchhoff law. Kirchhoff law is saying about the thermal equilibrium. The emissivity of a body is equal to its absorptivity when the body remains in thermal equilibrium. So that is called Kirchhoff law. Kirchhoff law deals with the thermal equilibrium, where the emissivity is equal to absorptivity. You know that emissivity is equal to absorptivity at thermal equilibrium condition. At all temperature, the ratio of total emissive power E to the total absorptivity is constant for all substances which are in thermal equilibrium. So that is the Kirchhoff law. So temperature, the ratio, at any temperature, the ratio of total emissive power to the total absorptivity is constant for all substances which are in thermal equilibrium. So here at the thermal equilibrium, the emissivity is equal to 1. So what happen if the emissivity is equal to 1? The body becomes black body. At thermal equilibrium, the emissivity is equal to 1. Then all the body becomes a black body. Therefore black body, you know that now only we saw that the absorptivity of the black body is equal to 1. Therefore the emissivity is equal to absorptivity. So that is the statement about the Kirchhoff law. Next, Weins displacement law. What the Weins displacement law states, the product of wavelengths, that is lambda max, here we are going to consider corresponding the product of wavelength corresponding to the maximum monochromatic emissive power and the absolute temperature of the black body T is constant. That is, the lambda max into T, which is equal to constant, that is 2989, sorry, 2898. 2898, we can say lambda into T, lambda max into T is equal to 2900 micrometer Kelvin. So lambda, the wavelength are generally in micrometer, therefore micrometer into Kelvin, this is the statement. So we can otherwise say is 2898 micrometer Kelvin, or 2898 into 10 power minus 6 meter Kelvin, like that we have to say. So the Stefan Boltzmann law and Weins displacement law are derived from Max Planck law of the spectral emissive power of the black body. So that you have to understand, the Stefan Boltzmann law, Weins displacement law, all are derived from the Planck's law, and this is the Planck's law. Planck's law deals with the monochromatic emissive power of the black body. According to this, the emissive power of the black body is equal to 2 pi c square h into lambda power minus 5 into e power ch divided by lambda into k into t whole minus 1. Here the lambda e lambda b is the monochromatic emissive power of the black body, and c is the velocity of the light. We know that the velocity of the light is equal to e3 into 10 power 8 meter per second, where h is the Planck's law constant, that is 6.625 into 10 power minus 34 joule second, where lambda is the wavelength, k is the Boltzmann constant, that is 1.3805 into 10 power minus 23 joule per Kelvin, where T is the absolute temperature. Here, the monochromatic emissive power of a black body is the amount of radiation energy emitted by the black body at the thermodynamic temperature T per unit time, per unit area, per unit length, that of wavelength. So this equation is furtherly sorted to the equation like this: E is equal to emissive power of the black body at all wavelength is equal to C1 lambda power minus 5 whole divided by e power C2 into C2 by lambda t whole minus 1, where C1 C2 are the constant. C1 is the 0.374 into 10 power minus 15 watt meter square, where C2 is the 1.4385 into 10 power minus 2 meter Kelvin. So this is about the Planck's law. Planck's law deals with monochromatic emissive power of a black body. Okay. And next is the Provest theory. Provest theory is a very simplest theory in radiation. It defines as the temperature of the body is more than 0 Kelvin, that is minus 273 degrees Celsius, then only the body will radiate. At absolute temperature there is no radiation. So that is the theory deals by Provest. So Provest says if the body is in absolute zero temperature, there is no radiation. Okay. Next is a Lambert cosine law. Lambert cosine law states that the total emissive power, that is E, from a radiating plane surface and in any direction is directly proportional to the cosine of the angle of emission. That is E theta is directly proportional to cosine theta, cos theta, where the proportionality constant is the radiation of the emissive power of the surface into cos theta, that is nothing but total emissive power. This equation is only true for the radiation surface whose radiation intensity is constant. Only for the constant radiation only this equation is valid. The Stefan Boltzmann law and Weins displacement law are derived from monochromatic emissive power. Thus, you have to understand that the point which is very very important, and the emissive power of the black body is pi times the intensity of radiation. Therefore, the emissive power of the black body we can say that is pi into L. L is the characteristic length. This is another formula for the emissive power of the black body. You can understand this. And next, whenever we study about the radiation, the shape factor, which is very very important, this shape factor and the reciprocity theorem, which is very very important for finding the radiation, the fraction of radiative energy that is diffused from one surface element and strikes the other surface directly with no intervening reflection, it is called a shape factor. The sum of shape factor is equal to 1, where the shape factor F is equal to heat transferred between 1 to 2 to the heat transfer by the 1, where the sum of shape factor is equal to 1. The sum of shape factor is equal to 1, which means that all the shape factor is less than 0.1. So this you have to less than 1, that you have to understand. What the reciprocity theorem deals with, if there is a two surface here, the shape factor and the area of the section 1 and section 2 are given. The area into shape factor of 1 to 2, which is equal to area 2 into shape factor of 2 to 1, that is heat radiated from here in this direction, which is equal to in this direction. Whenever the temperature is vary, the frequency, the shape factor is constant. So within these two bodies, this you have to understand. So the in the spectrum, if a body, radiative body, is in like a small direction, a small space where the room is there or any atmosphere is there, how much of radiation is being radiated by the small body, it is depends upon the shape factor of the body. So here this is the body 1, so this is the body 2. So area of the body 1 into shape factor of 1 to 2, it is equal to area of the body 2 into shape factor of 2 to 1. So this theorem is given as called a reciprocity theorem. So it depends upon the different plane surfaces. If it is a plane surface, the shape factor is equal to 0, where convex surface, again the shape factor is equal to 0, whereas a concave surface, the shape factor is not equal to 0. The shape factor is depends only on geometry of the body. So this you have to understand. The shape factor is depends on the geometry of the body, where the shape factor is between 0 to 1. Shape factor is between 0 to 1. The total sum of the shape factor is equal to 1. Okay, this you have to understand. When one body is completely enclosed inside the another body, then the shape factor of the inner body with respect to outer body is equal to 1. So this you have to remember that. And for the hemispherical body, the shape factor is equal to 0.5. For the cylinder, the shape factor is equal to 1. So this is the points to remember. So with this, I'm going to close today's session of radiation. I hope I have given an enough knowledge about this radiation. What are the contents I have delivered to you. So if you have any doubt, please let me know in the comment section. I will put another video for clarifying your doubts. So thank you all. Thank you for patient listening, and bye bye from Santhosh. Thank you all. Thank you once again.